Okay. So let's say the heavier one is there. We've now done 2 different measurements. So now you know the heavier one's there. So what?
So then you split the 2.
You split those 2 and you've got it, right? So 1 and 1, you're there, right? So 3 measurements is what it would take to guarantee it. So again, it's about critical thinking. It's about problem solving. It's about whether or not when you're faced with a problem, you have this like nervousness, like shit, or if you're like, okay, I got it. I've been here before. I've been confronted with something that I'm uncomfortable with. I can handle this. Let me just calmly rationalize it and think through it, right? Let me understand every word, everything that's presented. And this is what would translate well into a good employee, right? In the engineering field, right? You want to be able to give your employee a task and they're not like, well, can I go on to Google and go find the answer? No. Like, can they figure this out? Because in the real world, the answers aren't out there on some website, right? The answers are going to have to come from within you and your team, usually a team working together. Okay. All right, let's get down to business. I could keep talking all day, but we are here to learn calculus. So let's get to it. Any questions before we get started? I've got my list of students over here on the side. I've got you numbered, randomly generated. I'll give you a hint. Christian, you're going to be the first one I call on, and then it's going to be Sarah, and then it's going to be Nicholas, and then it's going to be Christopher and Alexis. I'm giving you the first 5, so I'm coming. Just be ready. All right. So this idea here about inverse trig functions, you may or may not have covered this already in Cal 1. So there might be a little bit, in pre-Cal, you talk about inverse trig functions. I should take that back. But we're not interested in inverse trig functions. We're interested in derivatives of inverse trig functions. So you may have already talked about the derivatives of inverse trig functions in Cal 1. You may have, it depends on your professor. But let's just get some things kind of squared away to begin with. We know already that if we take the sine function and we take its derivative, so I'm using the little prime mark for derivative. We all know the derivative of sine is cosine. We know the derivative of cosine is negative sine. We know the derivative of tangent is, who did I say was first? Christian? Is Christian there? I always got to.
Yeah, I'm here.
There you are. Okay, Christian. Derivative of tangent, Christian?
Secant squared.
Secant squared. Yep. Okay. Now, those are 3 trig functions and their derivatives. And then we have 3 more trig functions, which are just the reciprocals of those. And we have derivatives for each of those, right? Those 3 you should have up here, right? Their derivatives, you should have those. The others are cosecant x, secant x, cotangent x, and they all have derivatives. I'm not going to write them down. They're on your formula sheets, right? So where everyone should stand right now walking in here is that you understand that there are 3 basic trig functions and that each of them have derivatives. But in pre-cal, we learn that, and this is pre-cal, so this is 2 classes ago, we learned that every one of these functions has an inverse function, a function that undoes it, right? So for the sine function, there is the inverse sine. And we can write it as this, or we can write it arc sine. There's 2 different notations for the same function, right? And we have arc cosine, we have arc tangent or inverse tangent, we've got arc cosecant or inverse cosecant. So there are 6 inverse trig functions. So these are our trig, these are our inverses. Now, we also learned in pre-cal that when you talk about inverse functions, you have to be careful because you have to have domain restrictions in order to define an inverse function. So I'm going to start talking about that a little bit, but I just want you to know our goal here is to understand that each of these inverse trig functions, each of them, and there are 6 of them, okay? There are 6 inverse trig functions. Each of those 6 inverse trig functions has a derivative. And that's what we want to make sure we know today is what are the derivatives of those 6 inverse trig functions. So this first part here, 3.5, is just a review. So I'm going very quickly through this. When we're learning about functions, we talk about what are called one-to-one functions. And one-to-one functions are functions that pass both the vertical and horizontal line test at the same time. So in order for a function to have an inverse, it must be one-to-one. It must pass both tests, vertical and horizontal line test. But when you look at like the sine function is not one-to-one, right? It does not pass, well, it passes the vertical line test, but it fails the horizontal line test. You draw a horizontal line through there, it'll hit more than once, right? Let me try doing that. I'm doing this more from my own to make sure this was working properly. If I draw a horizontal line through here, then because I hit more than one place, that function does not have an inverse. And we're looking at the sine function, right? So it doesn't have an inverse. But I'm saying it does over here on the left. I'm saying, hey, yeah, it does have an inverse. Well, the reason is because we have to restrict the domain. And we do that in pre-cal, right? In pre-cal, we restrict the domain. So when we go to restrict the domain, what we do is we say, okay, we're going to not look at the whole sine function. We're just going to look at this one little piece of it. And if we look just at this piece in the middle, then that piece is one-to-one. And the entire range is in that little segment. All right, so if I take the sine function out of here, that little blue piece goes from -1 to 1, right? Every value in the range is included. And so just that little piece, on that little piece, we can define an inverse function. And so that's how we do it. We say, okay, we will define the inverse sine function so long as we agree that we're only going to look between -pi/2 and pi/2. So that's our domain restriction on the sine function. Between these two values, restrict the sine function there, and then you have its inverse. Does this all ring a bell from pre-cal? Okay, and then we can graph that function, and here's the graph. Here's the graph of sine. This is that function right here, this blue one. That's it restricted. And then if we graph the inverse function, that's what the arcsine function looks like. Okay, we're not going to get into the details of the graphing. Just want to have it there. So some examples we can do, just to make sure we understand what's going on here, is we can try and find some values of arcsine. So I'm going to do these examples here. Example 1, part A. If we want to know what arcsine of 1 is, I'm going to write it a different way, arcsine of 1. What we're asking ourselves, the question that this is asking is, well, maybe I should write it this way, just to make sure we're all on the same page. When you think about a function, you have the input, you have the output. The sine function takes in angles and spits out numbers, right? The inverse sine goes the other direction. It takes in numbers and spits out angles. So when we're asking ourselves, what's arcsine of 1, our answer should be an angle. It should be some angle theta. I'm going to call it theta. So this question really converts into the question, sine of what angle is 1? Okay, that's what we're really saying. So when you say arcsine of 1, what is it equal to? You're really saying sine of what is 1? So this is where it's, you know, how you solve this is going to depend on how you learned in pre-cal the different trig functions. And I've always been a proponent of the unit circle, and that everyone understands the unit circle, and that you've got it like almost hardwired into your brain. In my head, I always have this visual idea here of a unit circle. And I've already kind of memorized all of the values along this circle. And I hope that you've gotten to a point where you've memorized those. We have these points, 1, 0, this one's 0, 1. Well, I'll just do the first quadrant. If you go halfway, that's root 2 over 2, root 2 over 2. And then if you go, this is 30 degrees, that's 60 degrees, you have root 3 over 2, 1. And then you, not, sorry, 1 half. Then you have 1 half root 3 over 2. And then all the other points around the circle are just like reflections of those points, same values, just different signs. So the importance of the unit circle is that the X and Y coordinates tell you something. So like when I highlight this root 2 over 2, let's go to the next person on this list. Sarah, where's Sarah? Is Sarah here? There you are, Sarah. So Sarah, did you learn your trig stuff off the unit circle? Like, are you pretty comfortable with that, or was that not emphasized that much for you?
No, I did not. I went to a private university and they didn't really emphasize the unit circle.
Okay, okay. So are you familiar with, now I've got this up, are you familiar with the idea that on the unit circle, if you go to any arbitrary angle, let's say that this is the angle theta, that the points on that circle will always be cosine theta, sine theta. That the x coordinate is always the cosine of the angle that you're at, and that the y coordinate is always the sine of the angle that you're at. So that's the main connection that you have to have here. That x is always equal to cosine theta, and the y value is always equal to sine theta. Those are like the big formulas that I guess you need to know. So when you look at this up here, right? When you look at that, we're asking ourselves, sine of what angle is 1, right? We're really asking ourselves, where is y 1? Do you all see that? Like, where on the unit circle is your y coordinate 1? So where is it happening? Right there, right? See that? The y coordinate is 1. And what angle is that?
90.
90, right? So we are going to use radians instead of degrees. So we're going to answer in terms of like pi. So
Oh, it's pi over 2.
Is pi over 2. Okay, so the answer to this, I'll put it up here in the top left. Arc sine of 1 should be 90 degrees or pi over 2. We're not doing any calculus right now. This is more just like getting the gears going again, talking about pre-cal. Let's do another one. I might be able to squeeze this one in below. Yeah, let me try this one. So part B, we're going to do arc sine of root 3 over 2. Okay, so again, what we're saying to ourselves is sine of what angle is root 3 over 2, which really means where is your y value, root 3 over 2, on the unit circle? So who are we at here? I've gotten through Christian, we've talked to, and Sarah, we talked to, who was up next? Nicholas? Where's Nicholas? I'm looking for Nicholas.
I'm right here.
You're there? Okay, got you. How you doing, Nicholas? You sound tired. You all right?
Yeah, I usually wake up around 1 or 2.
It's a little early for you. All right.
Yeah.
Well, I mean, if anything's going to get you excited and wake you up, it's calculus, right? I mean,
True.
right? Okay. So, Nicholas, do you know where your y value on your unit circle is root 3 over 2? Do you know what that angle is in radians?
No.
Okay. Do you see on the unit circle a y coordinate that's root 3 over 2?
Yeah.
Okay. So it's right here. Do you know what that angle is?
60 degrees.
60 degrees. Now, in terms of radians, 60 degrees is really pi over 3. Okay, so our answer here would be arc sine of root 3 over 2 is pi over 3. Now, I have a question for you, because I didn't draw the whole unit circle, did I? I only drew part of it. If you were to continue drawing this and you went to the other side over here, right there, that's 120 degrees. Okay, the y coordinate there is also root 3 over 2. So why is the answer not 120 degrees? Why is it pi over 3 or 60 degrees? Why is
The
it not?
inverse sine.
Because you're in the first quadrant.
That's
and
right, because we have a restriction. Remember, our domain for the sine, if we're going to talk about inverse sine, we can only look between negative pi over 2 and pi over 2. That's the only thing we're allowed to look at. So when we're looking at this unit circle, when we're talking about the inverse sine, we have to throw away the whole left side of the unit circle. We're not allowed to look there at all. And that's why your answer has to be the 60 degrees or pi over 3. Let's do one more. I'm going to squeeze it in here. I'm going to do a part C, even though there's not one here. What's arc sine of negative 1/2? All right, so we talked to Nicholas. He's still waking up. And Christopher. Where's Christopher? Hey, how's it going, Christopher? I see you there. You doing all right? You awake?
Yeah, I'm awake. I'm just thinking.
Okay. Yeah, okay, so this is the same question, right? You're saying, where's the y coordinate negative 1/2? Any ideas?
It would be in the fourth quadrant.
In the fourth quadrant, it's going to be about right here.
So would it be
That's-
11 pi over, no, my bad. 11 pi over 6?
Okay, close, all right? I think everyone would agree with you that that angle is 11 pi over 6. If you were to start, I'm going to go with my big green highlighter here. If you were going to start at 0 and go around, then that would be 11 pi over 6. But that can't be our answer, because remember, we are restricted between negative pi over 2 and positive pi over 2. And so 11 pi over 6 is way too big. You've gone way too far. So what, instead of going all the way around like I did with the green, we actually just need to go backwards, right? We just need to go backwards by a certain amount. How much do we need to go backwards by?
So that would be negative pi over 6.
Negative pi over 6, exactly. So this would be negative pi over 6, and that would give us a y coordinate of negative 1/2. So you just have to be a little careful. You can only work in the first and fourth quadrant, but you can also only work with angles between negative pi over 2, which is straight down, to straight up. All right? Okay, now we have the inverse sine function. It has its own restrictions. Then we move on to the inverse cosine function. And when we look at the cosine function, we have different restrictions, right? If you go back and you look at, now I'm not going to review all of this, all right? When you go and look at the inverse cosine function, the restrictions we have are that you have to be between 0 and pi, not negative pi over 2 and pi over 2. It's between 0 and pi. And then there's restrictions if you want to define the inverse tangent function. And those are between negative pi over 2 and pi over 2. So you might want to go back and just review that a little bit. I just wanted to kind of remind you that every inverse function has domain restrictions. We have to be careful when we're trying to evaluate inverse trig functions. And we have 6 of them: arc sine, arc cosine, arc tangent, arc cotangent, arc cosecant, arc secant, all 6 inverse trig functions. Now we also have a cancellation property, which tells us that when you compose a function together with its inverse, they essentially wipe each other out. But again, we have to be a little bit careful with that. I just want to state the property. And now we get to the big deal, which is how do we find the derivative of a trig function, of an inverse trig function, all right? Whoa, what happened? Okay, so here's the main idea in 3.5. What is the derivative of an inverse trig function? So let's start out by writing down the first inverse trig function we have. So we are assuming right now that this is a well-defined function. I'm not writing f of x, I'm just writing y equals arc sine of x. And what we want to do is we want to try and find y prime. We want to know its derivative. So if that were just sine x, we just say the answer is cosine x. We learned that in Cal 1. But we don't have anything. Now, we could use our formula sheet, couldn't we? Like, we could break out the formula sheet. And we could go looking for it. We've got derivatives here somewhere. Here we go. Here are derivatives. Let me open this up a little bit. Here are the derivatives. Here are the inverse trig function derivatives. It's saying that the derivative with respect to x of arc sine of x, the answer is 1 over the square root of 1 minus x squared. Okay, that's the answer. But why? All right, where did that come from? Here's all 6 of them, all right here. So you don't have to memorize these, all right? But we need to see where they come from. And the reason we need to see where they come from is because the technique that we use to actually find the derivative is something that we're going to use later when we're doing something else. So to do this, to find out what the derivative of the inverse trig function is, we are going to have to use a couple of things from Cal 1. Something called a reference triangle and implicit differentiation. So these are things that in Cal 1 you should have covered. So I'm going to work through this. Y'all ready? Okay, the first thing I'm going to do is I'm going to realize I can't take the derivative of this function because I don't know the derivative of it, right? But here's what I do know. I know that if I were to compose the right side with sine, the sine function, if I were to do composition, I could use the cancellation property to get rid of the arc sine. So just follow me through on this. I'm going to essentially take sine of each side of the equation. So I'm going to take sine of the left side, and then I'm going to take sine of sine inverse of x. Now, there's no calculus there. That's just more of an algebraic move. So the left side becomes sine of y. And let me turn off that beep. I don't know if y'all can hear it. Every time someone comes and goes, it beeps. Okay. So the left side is just sine of y. The right side is what? So what happens? It's just x, right? Okay, now, at this point, what I'm looking at, I no longer have an inverse trig function in here. I've got a trig function, I've got sine, but I know the derivative of sine. So here's where I'm going to do implicit differentiation. So I'm going to take the derivative on both sides of this equation with respect to x. So I'm going to take the derivative on the left side of the function with respect to x. And then I'm going to take the derivative with respect to x on the right side. So the right side is the easier one. So let me call on Alexis. So Alexis, what is the derivative of the right side? Is Alexis here? No, I don't see Alexis. I don't see Alexis on my roll here. So since Alexis is not responding, I'm not going to count her today. So you see how this is kind of working? It's just I'm going to kind of just see if you're here or not. Let's see, who was it next up on this?
I can answer for Alexis if you want.
Yeah, sure. What's your first name?
Varun.
I'm looking because I want to mark you off here. There you are. Okay, got you. All right, what do you got?
So the derivative of x is 1, right?
Yes. Okay. Well, since you volunteered, what about the left side?
Oh
What is
god,
the
no.
derivative of what is the derivative of sine of y with respect to x?
Okay, so using my best judgment, I know the derivative of sine is gonna be cosine.
Okay, so I'm going to put
As
that
for
cosine of y.
as
That's right.
for do things get messy if there's a different variable? Would it be like y prime, or how would you take the
Exactly.
derivative of
Exactly.
y?
So this is chain rule. So what we're doing is we're going to be acting like the inside here, that y is just some junk. We don't even care what it is. So the derivative of sine of some junk is cosine of that junk. But then the chain rule says now you have to multiply by the derivative of what's in here. And the derivative of y with respect to x is dy dx. It's just dy dx. It's y prime. I can write it two ways. I can either write dy dx or I can write just y prime. It's kind of notation. You have the flexibility to use whatever notation you want here. But the whole thing, I'm going to write it that way first, then I'm going to rewrite it underneath with a different notation. Like this. I like the second notation because what was it we were trying to find? When we look back at the original question, find y prime. Now we actually have y prime somewhere now, don't we? And so all we need to do is isolate the y prime on one side of the equation. So we have y prime is equal to 1 over cosine y. All I'm doing there is dividing both sides by cosine y. Is everyone good up to that point? Okay, so we have solved. We know what y prime is. The only problem with our answer is that it's in terms of y, not x. Our original function was y as some function of x, and our answer is a function of y. So it would be really nice if we could rewrite that in terms of x, not y. So this is where the reference triangle comes in. So I'm going to try and draw a triangle. I don't think that draws a right triangle, never mind. So I'll just do it by hand. So I'm going to draw a right triangle. And what I'm going to do is I'm going to go back to this relationship that I have right here between x and y. And I'm going to use that information in this triangle. So let me draw the triangle first and label the sides, and then let's talk about why I did it this way. So everyone needs to understand why that right triangle represents what's in green here. So sine of an angle, sine is opposite over hypotenuse, right? That's what sine is. So if I were to ask you right now to look at this triangle and tell me what sine of y is, you would say that that's the opposite side, x over 1. So what I did is I started with the green over here, and I created the triangle based off that green equation. So I made the triangle fit perfectly into that green equation. Does that make sense? You have to kind of like reverse engineer it a little bit. Now, why is having that triangle important? We want to know what cosine of y is, don't we? But we have a right triangle now. So if I asked you to tell me what cosine of this angle is, you would say cosine of an angle is the adjacent side over hypotenuse, right? Now, can you solve for this adjacent side? If you've got two sides of a right triangle, you can always solve for the third one, right? So I'm going to trust that all of you could get this adjacent side and solve that it's this. All I'm doing there is, I'll do it, it's first time, okay. All I'm doing is this. I'm just saying, I'm gonna call that side, I don't know, B, okay? I'm using the Pythagorean identity, b squared plus x squared is 1 squared, and then I'm solving for b. So b squared equals 1 minus x squared, I subtract x squared on both sides, and then I take the square root. I only take the positive answer, because I'm talking about the length of a side of a triangle, so it's going to be positive, and that's where that short side comes from. We good with that? Okay, so what is cosine of y then? Cosine of y, according to this picture, would be, well, let's see. Let's go to the next person here. I've lost my place here. Oh, there you are. Coleman. Is Coleman here? There
Yes,
you are. Okay, Coleman.
the square root 1 minus x squared over 1.
Yep, it's the square root of 1 minus x squared over 1, but we don't really need to put it over 1, so we'll just leave it like that.
Right.
Now, Coleman, if you come back over here and you go to where we were solving for y prime, let's write the answer. It's just going to be what?
Square root of 1, sorry,
It's all right.
minus x squared.
Okay, what about, but that's in the denominator, right?
Right, so yeah, it'd be on the,
Yeah,
yeah.
1 over that, yeah. There it is. So that's what the derivative of arc sine is. And if we go back and look at our formula sheet, all right? Interesting, hold on. My thing's not working. Oh, I know what I did. Sorry, I'm still working some of these bugs out here. Okay, right? We just proved that formula. And all it took was a little bit of cancellation property, taking sine on both sides. Well, let's go back and review it. I want us to actually just kind of rethink through the whole thing. So we started out with the original function we wanted the derivative of. We took sine on both sides to get rid of that inverse trig function. We looked at that equation. We differentiated it implicitly. The right side was easy. The left side required some chain rule. We isolated the y prime. From there, we went back to our original relationship between y and x, created a right triangle off of it. Once we had the right triangle, we were able to recover what cosine of y was and then plug that in and we're done. Make sense? So if we were faced with this now and we wanted to start and go, okay, let's figure out what the derivative of this is. So if we're asked to find y prime here, then is it Jorge? Is that right, or is it George, or?
It's Jorge.
Okay, Jorge, how are you doing today?
Good. Good.
So do you kind of understand the process from last time?
Yeah, I'm getting the hang of it.
Okay, so what do you think we would do first here?
First, you have to put a cosine, so you, like cosine go to the y.
Yeah,
You have to multiply both numbers on both sides.
there we go. And then when we differentiate now, we take the derivative on the left, we would get derivative of cosine of something is negative sine of that times the chain rule again. You would have to take derivative of what's in here, which would be y prime, and then equals 1 again. So I didn't write d dx on this one. I just did it mentally. I took the derivative on both sides. So from this step to this step, I'm taking derivative with respect to x. We isolate y prime. So I divide both sides by negative sine y. And now I need a triangle, right? And I'm going to go back and look at, let me ask someone where I'm going to look. How about Jane? Is Jane around? Hi, Jane.
Hello.
So are you okay? Are you following this okay so far, Jane?
I think I am, yeah.
Okay. So I'm going to draw a triangle. So where am I going to look? What equation am I going to look at to generate this triangle? Which equation gives us a nice relationship between y and x? What's that?
Those
So let's just look
Oh,
at the equation.
it was the cos y equal x, right?
Yep, that one right there. That one gives us a good relationship right there. So what I'm going to do now is I'm going to go to my triangle. I'm going to put the y here because y is the angle. Cosine is which side over which side? Adjacent over hypotenuse, right?
Mm-hmm.
So you're off the hook, Jane, by the way. So who wants to tell me, let's see here. I'm trying to get through everyone today. Peggy, is Peggy here? Peggy,
Yeah.
going
Yeah.
okay?
Mm-hmm.
Can you tell me how to label this triangle? Like what's the value of the hypotenuse, the adjacent side?
When the hypotenuse, hold on, I think the adjacent side would be x and the hypotenuse would be 1.
Yep. Okay, good. So that's using the fact that this up here, this green thing is really saying x over 1. So if you want to say cosine of something is adjacent over hypotenuse, then the adjacent's x and the hypotenuse is 1. And then
And
that
then
allows,
the remaining side would be what we found out last time.
yeah, it's the same thing, right? It's this. And so can you tell me, you can just keep going, Peggy, if you
Oh,
want.
okay.
What's
I'm
sine?
also writing it down.
Yeah, that's okay. What's sine of y then?
It would be the root of 1 minus x squared over 1, I think.
Over 1, yeah, over the hypotenuse. So that's your sine y. And all we got to do now is take that and plug that in here. So our answer will be 1 over negative square root of 1 minus x squared. Very close to the derivative of the inverse sine function, isn't it? The only difference is a negative down here. Everything else is the same. And if we go back and we look at the formula, you'll see here that, oh, it's right here, right there. It's the same as this one, but it's got that little negative right there. They just push the negative out front. But do you see how that's the same as this one? Okay. All right, now I'm not going to do the rest, okay? Because there's 4 more to do, right? But each one of them would be the same thing. You would take if we were doing arctangent, you would take tangent on both sides. Then you would differentiate implicitly. Then you would solve for y prime, and then you would draw a right triangle, and then you'd figure out what the sides are, and then you'd plug your answer in, you get some algebraic expression. Okay? So we have the derivatives of the inverse trig functions. They're all on the formula sheet, all right? I'm not gonna ask you on a test to derive a formula. Again, this was more of an exercise just to see how we can use implicit differentiation along with reference triangles to get through a problem. What we're more interested in right now is using these derivative formulas from the formula sheet to be able to take derivatives of more complicated things now, using chain rule and things that we've learned in the past. So let's start a new page. And I think for the sake of making this a little easier, I'm going to grab all these formulas, drop them into our page. Oh, wrong button. All right. So the first problem that I want us to do is this one right here. So we're going to try and find the derivative with respect to x of arc sine of the square root of 1 minus x squared. So what we're doing right now is we're done trying to figure out what the derivatives of the inverse trig functions are. We know their formulas now. Just like you know the derivative of sine is cosine, now you know the derivative of arcsine is 1 over the square root of 1 minus x squared. Okay, so now that's all kind of in our toolbox. Now let's try and find the derivative of this. So what we need to do is chain rule, right? We have arcsine of something. So the derivative of arcsine of something should be equal to 1 over the square root of 1 minus, so I'm just using this formula right here. But what comes next? Because I'm not taking the derivative of arcsine of x, I'm taking the arcsine of all that square root of all that crap. So
You substitute that into the equation, into
yes,
x.
yes. So we're actually going to replace the x with all of that stuff. I'm going to mark you as participating, Yosef. Am I saying that right? Yes, Yusuf?
Yes, sir.
Okay.
Yusuf.
Is it Yusef or you say it?
Yusuf.
Yusuf. Okay. Yusuf. All right. So we're going to be taking everything that I had in red here, and we're going to be replacing that x in the formula with that whole thing. So we have to take it and square it. So what happens when you square that?
It cancels out.
The square root goes away and you get 1 minus x squared, right? Are we done? We are not done. All we have done is the outer layer of the chain rule. We've taken the derivative of the arcsine of something. Now we need to move in. Oh, crap. Now what we need to do, we've taken care of the derivative of this part. What's the next function on our way in? It's that square root, right? So we have to take the derivative of the square root of something. What is the derivative of the square root of something? So this goes back to Cal 1. If you have square root of x, what's the derivative of that?
1/2 over 1/2 x to the power of negative 1/2.
Yep, there you go. Now, a lot of you learn it that way because you're taught that square root of x is really x to the half. And then you use the power rule, right? The half comes out, you subtract 1. In my Cal 1 classes, I do show that, but I have them memorize it a different way, and I do have them memorize it. I always tell them the derivative of the square root of x is 1 over 2 square root of x. It's the same answer. It's just written with the square root and it's dropped down. So it's just taking that negative exponent, pushing it down to the bottom and rewriting it in radical form. I like having it memorized that way because when I get to something like this, to me, it's just easier to use. So what I'm going to do is I'm going to say, okay, I'm taking the derivative of the square root of all that crap, right? So my answer should be 1 over 2 times the square root of all that crap in here that's in yellow. Am I done? Nope. Now I've got to still do chain rule times the derivative of the next layer in. So now I'm taking care of the square root. The next layer in is the 1 minus x squared. I have to take the derivative of that. And what is the derivative of 1 minus x squared?
Negative 2x.
Negative 2x. Okay, there it is. Now let's try and clean it up a little bit because it is kind of messy. Any questions though on how I got that? If you're like sitting there going, oh my God, then you just need to go back and tighten up your derivative review a little bit. I sent an email out today about the tutoring labs, or a Zoom link to get to the tutoring lab. If you want to get tutoring, they just click on that link and they have their hours up there and they have live tutoring. Okay, clean it up. Let's do this first. So that's going to be 1 over the square root. Don't those ones cancel? Those ones cancel, don't they? It's 1 minus 1 plus x squared. That's what winds up happening.
Yeah.
And then I have times, and then over here, these 2's cancel. And I have just a negative x on top, and on the bottom I have the square root of 1 minus x squared. Now I know that some of you are going to want to turn this thing right here into x. I know that that's a very, very tempting thing to do.
Wouldn't that be negative x squared?
Where?
The green, just because the 1 and 1 goes away, but you're still left with that negative?
Well, there was no negative because remember this negative has to distribute through. So the minus minus would become the plus. Good call. I'm glad you mentioned that because it's important that I put this in parentheses. If you didn't put that in parentheses, then you would have not had that distribution that would have caused issues.
On top, why did you cancel out the 2 and then the negative 2?
Just reducing it, like, you know, 2 over 2 is 1. Just trying to clean it up. I mean, I left the negative there, but I just got rid of the 2's. So technically speaking, what is the square root of x squared? It's not just x. Does anyone know?
It's 2x. Or no, derivative.
It's the absolute value of x. Okay? The absolute value of x. That's the definition of it. The reason why that's important is because if you had just written that that was x, then wouldn't you try and cancel it? Like had you made this an x down here, then you would have tried to have canceled that out with that x up top. And that's not right. Whoa, what happened? Okay. So that's pretty much it. I mean, we can't really go any further with this. We could put it all into one fraction, but we'll just leave it like that. Okay, so the point of that example was just to illustrate how now that we have these 6 new derivatives, they're in play, right? Anytime we see something with an inverse trig function, we should be able to take derivative, even if it involves product rule, quotient rule, chain rule. It's all fair game now. All right? Okay, we have another one here, another example. I'm going to leave that table up there. I think what I'm going to do is I'm going to squeeze this one in here by moving this one down. Okay, so now we're going to try and find the derivative of this. Y equals the square root of natural log of arctangent of x. More chain rule. See, I'm trying to throw as much chain rule at you as I can right now because, like I said last time, you know, the ultimate goal in the first third of this course is for us to be able to go backwards. So you've got to be comfortable going forward before you can go backwards. So we've got to be able to take derivatives. So here, this is a composition. We actually have 3 functions composed together. The outer function is square root. Inside that, we have natural log. Inside that, we have arctangent. So we're just going to work our way from the outside in. So the derivative, I'm going to focus my attention on the square root part first. What is the derivative of the square root of something? Let's go to Jimmy. Is Jimmy around? Jimmy, yeah. Okay.
Yeah, I'm right here.
All right, Jimmy. You doing all right today?
Yeah, I'm doing good.
Okay. So derivative of the square root of all that crap in there. What do you got for that?
I can't tell you. It's like a refresher for me, like trying to do everything.
Okay, that's fine. So let me put something over here for everyone again. I want you to, Jimmy, to try and burn this into your brain between now and next class. The derivative of the square root of something is 1 over 2 times the square root of that something. All right? That's the kind of formula you want to have down. So with that, Jimmy, if I'm going to be taking the derivative of the square root of something, The something I'm referring to here is everything in green. The derivative should be 1 over 2 times the square root of the something, right? The stuff in green. So that should be natural log of arctangent of x. Before I continue, let me just kind of say something. In Cal 1, when you were doing chain rule, when you first learn chain rule, you learn all these different ways where you can like write it out as a composition of functions and then use formulas to take derivatives. I hope that your professor at the time told you that the ultimate goal with chain rule was for you to be able to do it without having to write all that stuff down. Like you should be able to work through it kind of like I am right here, just kind of layer by layer. So if you're still at that point where you have to do the chain rule by writing a bunch of different things down and kind of cranking away through it, that's okay, but everything is going to go slower for you, all right? That's just the way it's going to be. So you want to try and speed that up. If you want some help on chain rule, you should come to my office hours. I'll show you kind of a shorter way to learn it, or go watch my old videos, whatever. Okay, we're not done. Times. We have taken care of the square root. Let me erase some of this. Ah, shit. Didn't want to do that much. Okay, so we have taken care of the square root. So we don't have to talk about that now. The next layer in is the natural log. So we need to multiply by whatever the natural log, we have natural log of some stuff. And Jimmy, let's see, Cheyenne, is Cheyenne here? Yep, hey Cheyenne. Doing all right?
Yeah, I'm doing good.
Okay, so do you remember from Cal 1 what the derivative of the natural log is? The derivative of the natural log of x?
No.
Okay, so be aware, everyone be aware that's on your formula sheet, but this is one of the this one you should have memorized. I'm not saying like today, but like from here on out, you should have this one memorized. Who can help?
Isn't it 1 over x?
It's just 1 over x. 1 over x. So the derivative of natural log of something is just 1 over that something. So for us, the derivative of natural log of arctangent of x is just 1 over arctangent of x. All right, we aren't done. We've now taken care of the natural log part. We're at the last layer of the onion here. We want the derivative, and this is going to be Michael. Is Michael here?
Yes.
Sandoval? Okay. All right, Michael. So the derivative of arctangent of x. I haven't even told you all, right? But look at the page. Do you see it there? So this is one of our new formulas, right?
1 over, yes.
Yep.
1 over 1 plus x squared, yeah.
Yep, 1 over 1 plus x squared. So that's a new formula for us. Times 1 over 1 plus x squared. And that is our derivative. Yeah, we could try and clean it up a little. We could probably push everything into one big fraction. Like I could put parentheses here and then make it like one big division bar and then replace this with a 1. But there's not a whole lot more I can do. I mean, that's just one big ugly ass function, right? But that is the derivative. Now I'm going to put a star on this formula that Michael just used, arctangent. I lied. I'm putting more than 1 star. I'm putting 5 stars. Burn that in, okay? Burn that into your brain. The derivative of arctangent of x is 1 over 1 plus x squared. All right, burn it in. That is the most commonly used derivative in this class when we deal with inverse trig functions. You may see the other 5 here, but that one there is going to pop its head up so many times The sooner you memorize it, the better, right? All right. We are moving on unless there's a question. New page. You know what? Hold on. Let me go back here. Let me grab this and bring it over. It's working out pretty good. I like that. Are you all able to see my screen enough? Like, am I with the space I'm drawing in, can you make out what I'm writing? Is it clear?
Yeah.
I mean, if you're on a phone,
Yeah,
you're probably gonna have some trouble, but we're okay. So I have a huge screen here. I think this is like a 23-inch screen that I can write on. So for me, it's like I see everything, but I just want to make sure on your end you're okay. Okay, the next one. Find the equation of the tangent line to this at this point. So we have a curve, arc sine of x, y squared plus x plus y, and we want to look at the point 0, 0. So now we're starting to go a little bit beyond just taking derivatives. We want to do some stuff that we did back in Cal 1, finding the equation of a tangent line. So I'm going to take a moment right now to bring up Desmos, our good old graphing utility that's available to all of us. And I'm going to type in that equation. It was arc sine x, x times y squared. Nope. X times y squared equals x plus y. Did I get that right? Yeah. So there it is. That's the curve. That's what that thing looks like. And what we want to do is look at the point 0, 0, which is the origin, and I want to know the equation of the tangent line through that point. So we should be able to come up with an equation of the line that goes through that point and is tangent to the curve. You ready to do it? So what we need to know, if we're going to find the equation, right, of the tangent line, we can use this good old formula, the point slope formula, y minus y1 equals m times x minus x1. That's the point slope formula for a line. In order to use that formula, all we need is a point on the line. Do we have a point on the line? We do, right? We have the point 0, 0. You need a point on the line, and you need the slope of the line. Where are we going to get the slope from? We need this to be a tangent line.
Don't you get it from taking the derivative?
That's right. It's going to come from the derivative of that equation. So this is going to come from the derivative of the equation at the value 0, 0. So we got to find the slope of that tangent line at that particular point, which means we need to come back over this equation and we need to say to ourselves, what's y prime, right? That's really what this is. This is y prime at 0, 0. So that's what we're going to try and go for here. So how in the world are we going to take the derivative of that? Well, we can do it. This is an equation. We can take the derivative implicitly on both sides of the equation, just like we did in Cal 1. Just take the derivative. So I'm going to take the derivative on the left side and the derivative on the right side. So let's start on the left side and let's move on to our next volunteer. Stephanie? Yeah, Stephanie's here. Okay, Stephanie, you doing all right?
Yeah.
Okay. So Stephanie, on the left-hand side, we are taking the derivative of arc sine of some junk. What is the derivative, Stephanie, of arc sine of some junk?
So it would be 1 over the square root of 1 minus, and then you would put in the xy squared.
Xy squared.
And
but
then
that
square.
all squared, right?
Yeah.
Okay, and that's it. That's the derivative of the arc sine part. Are we done on the left side though? What do we still have to deal with?
The
junk, right? The yellow. Okay, so I'm going to put a times here, and Stephanie, I'm going to move on to our next victim, which is going to be, is it German?
Yeah, German.
German? Okay, I like that name. That's cool. All right, do you like that name?
Yeah, I like it.
Okay, good. All right, German. So German, we've got to take the derivative of this yellow part to finish off the chain rule. So what do you see in there that we're going to have to use in order to take the derivative of x times y squared?
Well, if it's asking for the sine minus 1, are we going to use that same equation?
Well, we did that. We already did the derivative of the arc sine. That's this part, okay? What we're focusing our attention now on is this part in yellow. So we've got to take the derivative of that. German, do you see in there that we have multiplication between those two things? X times y squared. And in Cal 1, when we have multiplication, we take the derivative, you got to do what?
Take the derivative of one of each one.
Okay.
Product rule.
Individually, or is there a special rule we have for products?
There was a special rule.
Yeah, it's our product rule, right? So we've got to do the product rule on that product. And so I'm going to throw it into parentheses here. So when we do the product rule, if you have two things multiplied, then it's always the derivative of the first one times the second, plus the derivative of the second one times the first one. And there's different ways you can write that, but everyone should have that. That product rule should also be hardwired, I think, at this point. So I'm going to work through this. I'm going to go the derivative of the first one, which is the derivative of x, which is 1, times the second one, plus the derivative of the second one. In German, you're off the hook. Alejandro? Is Alejandro here?
Yeah, I'm here.
Okay. Oh, there you are. Wait,
Yeah.
So you go by Alex, yes?
Yeah, I go by Alex. Yeah.
I'm going to change it in here so that I call you Alex next time. So Alex, derivative of y squared. You gotta be a little careful with this, right? What is it?
2y.
2y. But there's something else.
And you got to multiply by x.
That will come. That'll be at the end.
You need to multiply by y prime.
You got to multiply by y prime. So the way you look at it is when you're taking derivative of y squared, the first thing you're doing is you're bringing the 2 out, you're subtracting 1, but then you have to take derivative of y itself, which is not 1, it's y prime. So you've got a little bit of chain rule here, and this in Cal 1 is probably, whoa, what the hell? This is probably the part of Cal 1 that causes a lot of people problem when you're doing implicit differentiation, is that little y prime that pops out right there. So the derivative of x squared is 2x. We all agree with that. But the derivative of y squared is actually 2y prime. I should say that again. The derivative of x squared is 2x if we're differentiating with respect to x. If we're differentiating with respect to x and we take derivative of y squared, it's 2y prime. We've got that extra little y prime there. So that's our left side. Now we're done. We finished the arc sine part's done, and now the product rule's done. Now we can say equals, and now we take derivative of the right side. So what is the derivative of the right side? We are moving on to Maribel. Is Maribel here? Hey, Maribel. Can you hear me okay? I can't hear you.
Can you hear me now?
Oh, yeah, it's okay. I don't want you to have to yell.
I'll have to yell.
No, that's good. Okay, I can hear that. So on the right-hand side, you have addition, Maribel, right? So you can just do the derivatives individually. So what's the derivative of x?
1.
1, and then plus what's derivative of y with respect to x?
Y prime.
Y prime. Okay, good. All right, there it is. There's our derivative. That sucks. Okay, what are we supposed to do with this now? Remember what our goal
Plug in
was?
the point 0, 0.
Yeah, so
Isolate
we
y.
wanted to know what the derivative was at 0, 0. And so I do not recommend at this point that you go try and solve for y prime. What I would do is replace all your x's with 0 and all your y's with 0, and let's just see what happens. So I'm just using the fact that x is 0 and y is 0, and I'm just going to replace everything. So what does this all become? This just becomes a 1, doesn't it?
Yeah.
Times, what does all this become?
2, 1, all 0.
Y
That's all-
prime.
It's going to be 0, right? No, the y prime gets killed because x and y next to it are 0. So everything there gets killed, doesn't it?
Yeah.
Yeah.
So you just get 0 equals 1 plus y prime. So you have 0 equals, because those are multiplied on the right side, that. So what's y prime? Negative
1.
1.
Negative 1.
Move the 1 over. So the slope of the tangent line at 0, 0 should be negative 1. So then I come over here to this. I'm ready to plug everything in. Y minus y1 is 0 equals the slope, which is negative 1, and then x minus x1 is 0 also. So I'm plugging in the 0, 0 here for the x1 and y1. And when you put all that together, all you get is y is negative x. That's the equation of the tangent line. So if I go back to Desmos and I say, okay, Desmos, go ahead and graph me y equals negative x. There it is. It looks like we got it right, yes? We found the equation of the line that is tangent to that curve at that point. Oops, wrong one. How are we doing on time? Y'all hanging in there? You'll be all right. Okay, this will be probably our last problem here. Hold on, there was something I wanted to say. Kind of break up the monotony here a little bit. I'll tell you a quick little story. So we were just talking about how when you take the derivative of x squared, your answer is 2x. And that's what most Cal 1 students would be comfortable with. But we just talked about that when you take derivative of y squared, you get 2y prime. And the reason that that's the case is because in this scenario, we were implying, we never said it, but we were implying that we were taking the derivative with respect to x. So when you take derivative, the 2 comes down times x, but then you're supposed to take derivative of what's in here. And what is the derivative of x with respect to x? So what is the derivative of x with respect to x?
1.
It's just 1. And that's why your answer here is 2x. But this one, we're taking derivative with respect to x of y squared. You have the 2 come down, you've got the y, but now you got to take derivative of y. And so you get the derivative of y with respect to x, which is not 1. That's your y prime, right? So that's why that just happened a second ago. So this part right here, we're kind of leaving that out, right? When I say what's the derivative of x squared, I'm leaving out, I'm saying with respect to x. Because in Cal 1, we pretty much start doing everything with respect to x. So the story is this. I'll try and make it short. This will take about 3 or 4 minutes. So when I was in graduate school studying math, I pretty much had no no social life at all. Okay. I was in my early 20s and basically lived at school. I had an office because I was a teaching assistant at the university. And so I had a little cubicle with about 8 other teaching assistants. And I had a little bench, and I would sleep there, like just sleep there and wake up and just study. And we had chalkboards everywhere, and I'd just be doing my math. My parents would have to come like visit and bring me food. They, you know, it's just, if you ever go to grad school, you'll understand, like it becomes everything you do. So I had this kind of rule that like once a month I would go out and I'd meet up with my friends, and we'd go out to, you know, clubs and stuff. And I like to go out and I like to just get just completely crazy just for one night, you know. But the deal was that like I couldn't date anybody, you know, like I didn't have time for anyone, you know. It's just realistically, unless they were going to study math with me, there was no room in my life for that. So anytime that I would be out at a club and I never really approached women because I knew I couldn't offer them anything. So if by chance a woman approached me, I had like a minimum question that I would ask them. And I know this is like, looking back on this, this is very arrogant and it's very stupid, but I had a minimum math question that they had to be able to answer for me to even be able to have a discussion with them, because that's all I wanted to talk about was math, right? So my minimum question was, what is the derivative of x? Okay, yeah? Seem like a fair question? Derivative of x. So this one particular night I'm out there at this club, and I meet this girl, and we dance on the dance floor together for like an hour. We don't even say a word to each other, we're just dancing together, right? And I go to the bar, and I can't, this is all being recorded, this is terrible. Okay, so I go to the bar, and she comes up and talks to me, and I ask her, I said, hey, I just have to ask you a question. I said, what's the derivative of x? And she goes, with respect to what variable? And I was like, oh, okay. So she understands that that part of it matters, right? Like with respect to what variable, because the answer is 1 if it's with respect to x, but if it's with respect to t or something else, then the answer is, you know, dx dt. So I knew right away, she knew that. So I asked her a second question just to see like how far this could actually go. I asked her, I said, if you take, I'll draw the picture. If you take the interval 0, 1, take all the numbers between 0, 1, and you randomly pick a number out of that interval, just go grab one randomly, what's the probability that it's a fraction? So the way I proposed it to her is this. I just said, what's the probability of picking a rational number out of the interval 0, 1? That's exactly the way I posed it to her. What's the probability of picking a rational number out of the interval 0, 1? And her answer was 0. So so think about that. If you reach into the interval 0, 1, you just like randomly grab a number. The probability that you have a fraction in your hand is 0, and that's the correct answer. And I was like, holy shit, like she knows like measure theory. Like that's, so we wound up talking, dancing the rest of the night. She happened to be in town for a friend's something for one night. She was leaving the next morning. And so that was the last time I've ever seen her in person. Left that club, said bye to her. We exchanged email addresses because that's all we had back then. And I still talk to her this day. I didn't marry her. Everyone always asks me if I married her. I didn't marry her, but I still keep in touch with her. She programs the robots that weld cars together on the assembly line. So like when you go and you have a manufacturing plant that opens up, they bring in the computer science people and stuff. She goes and sets up all the equipment so that when the raw stuff comes down the assembly line, all the robots go and do all the welding and stuff. She's in charge of that procedure. So she's a very smart girl, but I tell the story because with respect to what variable, that is a very, very important idea here. It really is. And it's something that I really tell the story to my Cal 1 students, because when I'm trying to teach them implicit differentiation, this dy dx, dy dt, that with respect variable is super critical. And so when I tell this story, I think it sits, like it sinks in a little bit more, because you actually can like imagine me sitting there telling this, talking to someone, as opposed to me just putting it up here like this. So interesting to me. I still love telling that story. Blew me away. Couldn't believe she knew that answer. All right, you ready to do this word problem? We have 10 minutes. Okay, so this word problem is a related rate problem. And you could do this problem right now without anything we've done today, all right? But we're gonna use some stuff we learned today, and I'm gonna hopefully convince you why it's useful. Okay, so a rocket is fired straight up with a speed of 1,000 miles, or at a speed of 1,000 miles per hour. An observer who is a mile away from the launch point is tracking the rocket with binoculars. At the moment the rocket is 3 miles high, how fast is the observer's angle of inclination changing? What is that in degrees per second? Okay, so let's just first get a general picture of what's happening. So when I do related rate problems, I usually have a couple of things I get down. I get, first of all, a general picture. Then I do an instant picture, which is more like a picture. The first picture is like me imagining everything moving. And then the instant picture is like me taking a snapshot in time at a specific moment, because this wants to know something about a specific moment. It says at the moment the rocket is 3 miles high, how fast is the observer's angle of inclination changing? So 2 separate pictures. Then I like to write down what I want, or sorry, what I'm given. Then I like to write down what I want. And that's what I usually start every related rate problem with, right there. So the first thing is my general picture. I've got a rocket that started on the ground. So here's my ground. Here's my rocket. It started, let's say at this point, and started moving upward. And that rocket is somewhere up here. And I'm not going to draw a fancy rocket. I'm just going to draw a dot, if that's okay with you. So there's my rocket. It's moving up. It's traveling at 1,000 miles per hour. And then I have an observer that's on the ground, and they are watching that rocket. I know that that observer is how far away?
The mile.
1 mile. It says right here, a mile. So it's 1 mile here. Is watching that rocket, and they're watching it with binoculars. And so I'm going to kind of imagine that their sight of their binoculars is locked onto that rocket. And that creates an angle of inclination here that I'm going to call theta. And I'm not going to fix theta because theta is changing, isn't it? Theta is changing as the rocket moves up. I think that that's a pretty good picture right now. I can also call, let's say the rocket, how high up it is. Let's call that h. That's the height of the rocket. And the reason why I want to label h is because in my word problem, it talks about this moment in time when the rocket's 3 miles high. So in my general picture, I'm going to leave it as h because I'm imagining that the rocket's moving. But in my instant snapshot picture, I'm going to fix that h to be 3. So I'm going to draw another picture underneath here. And at this moment, the rocket is 3 miles here. It's not drawn to scale. My observer is 1 mile. Now tell me about this. In this instant snapshot picture, is theta changing anymore, or is theta fixed?
It's fixed.
It's fixed. Now I don't know it right now, but it is a number, okay? This is a number, and I could go figure out what it is. I could use some trig functions to do it, because I actually know what the opposite and adjacent sides are, don't I? So if I know 2 sides of that right triangle, I should be able to recover the angle. I could use some trig thing on my calculator, but I'm not going to. I'm just drawing this picture. Okay, so what am I given? I'm given the speed of the rocket, right? And the speed of the rocket, speeds are always rates of change, and rates of change are always derivatives. So the 1,000 miles per hour is the change in what here? What is changing at 1,000 miles per hour?
Speed, distance.
The height?
The height of the rocket, right? So if I'm looking at this in terms of variables, this h is the thing that's changing at 1,000 miles per hour. So when I write down what I'm given, I'm going to say, hey, look, the change in h with respect to time is equal to 1,000 miles per hour. Would y'all agree with that? I'm given how fast h is changing, because that's the rocket. What else am I given? That's about all. I mean, I'm a mile away. That's about it. What do I want? What is it asking for? What is the question asking us to find?
How fast the angle of inclination is changing?
How fast is the angle of inclination changing? When it says how fast, we're talking about a derivative, right? A speed. So what we want in the problem, I keep doing that. I need to move that button, it's in my way. What I want here is how fast the angle, which I've called theta, is changing with respect to time. That's what I want. And when do I want that? At exactly the moment what?
The rocket reaches 3 miles?
The rocket is 3 miles high. So I want that at exactly the moment that h is 3. Okay, so recap. I know my rocket's moving, right? Here's a snapshot of the exact instant in time. I'm given how fast h is changing with respect to time. I want to know how fast the angle's changing with respect to time, and I want to know that at exactly the moment that the rocket is 3 miles high. Now, at this point of a related rate problem, your next task is to try and find any equation you can think of, anything out there that somehow relates the variable h to the variable theta. And you have to go back and look at your general picture to find that relationship. So can somebody give me any relationship from anywhere in any class that you've taken in the past that somehow connects theta and h together?
Tangent.
Tangent, good. So if I wrote down tangent theta, what would tangent theta have to be according to that picture up there? Tangent is opposite over adjacent, right? So h over
1.
1, right? H over 1, which is just h. We have a relationship. Once we have this, we take the derivative with respect to time. So we're going to now take the derivative with respect to time on the left and the derivative with respect to time on the right. I know that y'all haven't done related rates in a while. Hopefully me going through this is kind of like bringing things back. What is the derivative of tangent theta with respect to time? So first, what's the derivative of tangent of something?
Secant squared.
Secant squared of theta. Is that all? Do we need more here? Chain rule. You still have to take
Can you find the derivative of theta?
You have to figure out what the derivative of theta is with respect to time. But actually, I don't need to figure out what that is, because that's what I actually want to know, isn't it? Like, I actually want to know what that is. So it's a good thing it showed up here because I need to solve for it. We're done on the left side. Now, what is the derivative of h with respect to time? Well, it's whatever the hell the derivative of h is with respect to time. Why am I not concerned about that, though?
Because we have it.
Because we have it. We know what it is. It's 1,000, right? So take a look at where we are. We have an equation where, first of all, what we're looking for is there, d theta dt. dh dt is here, which we know. And so the only thing really left to do to figure out what d theta dt is to figure out what theta is, right? If I could figure out what theta is, then I could answer this question. But theta, I'm going to have to get it from this triangle, right? You'll see that? I'm going to have to go use some tricks. So although this works, and I could keep going, I need to show you why this is not the most efficient way. So I want you to just rethink this problem. What is it that we wanted to know? D theta dt, right? I'm almost out of time. I am out of time. Here's what I'm going to do instead. I'm going to take inverse tangent on both sides. Shouldn't have told my story. I was trying to give us a little mental break. So I'm still working with the same equation, but I'm going to take inverse tangent on both sides. And the reason I'm doing that is because the left side now becomes just theta. And the right side is arctangent of h. Y'all follow? Now take the derivative with respect to time. Now do it. And so what is the derivative of the left-hand side with respect to time? Well, that's just d theta dt, isn't it? And on the right-hand side, now we have an inverse trig function. So what's the derivative of arctangent of something? You'd have to go back and look at that formula, right? That's the one I asked you to burn in. I put 5 stars next to it.
1 over 1 plus x squared.
H,
or
yep,
h
in
squared.
this case, it would be h squared. Now, one more step. Don't forget, we have to do chain rule. We have to take derivative of what's inside and tack it on here. It's dh dt. Now, what's better about this answer? What is better? You still have d theta dt, right? Which is what we're looking for. But what's better about what you see on the right side?
There's no secant.
Yeah, you don't need theta to get the answer, do you? All you need to know is what h is. Do we know what h is?
Yes.
Yeah, it's 3. Okay, do we know dh dt?
Yes.
Yeah, it's 1,000. No, see, by just doing that one little step with the arctangent on both sides, we created something that we didn't have to go do additional work to find theta. It was just more efficient. But it required that we knew what the derivative of arctangent of something was, which is what today was about. So it just shows you that problems that you've done in the past, perhaps there were more efficient ways to do them. And now that you've got these inverse trig functions, you know, it's all on the table. Okay, I have to stop because I can't keep y'all here forever. All we did today was 3.5. So the homework for 3.5 is what I would expect that you go through for next time. All right. And let's see, it's Wednesday. Isn't Monday a holiday?
No, you have it on your calendar that it's Labor Day, but it's until the 7th.
Do I have that one? I have it 1 day off or 1 week off, don't I?
Yeah.
Oops. Okay. So yeah, we will be here on Monday. We will be off the following Monday. I don't know why I messed that up, but okay. So when we come back on Monday, we're going to crank out 3.6 and then keep proceeding. All right. Y'all have a great one. If you have any questions, I'll hang out here for a few minutes if you want to hang out and talk to me about anything. Thanks for your participation today.
I have one question. And
Yes.
it was pertaining to your story.
Yeah.
Why was it 0? The probability?
Oh yeah. Okay. So
A fraction between 0 and 1 every time.
yeah. Okay. So here's I'm going to try and make this as easy to understand as possible. It's not real easy to do though. Okay. So if you think about fractions, right? So, you know, look at all the different fractions in here. 1/2, right? 3/4, and then you got 1/4, and then, you know, you could go on forever, couldn't you? I mean, there are an infinite number of fractions in here.
Sure.
Infinite number. But the problem is that's not the only stuff that's in there. There are things in that interval that are not fractions. And they're what we call irrational numbers. So we have rational numbers, which are basically fractions. And the thing that makes a rational number is that it can be written in a way where you either have a terminating decimal or a repeating decimal with a pattern. So like, here's an example. If we take the fraction in there 1/4, that's 0.25, right? Yeah. Okay, if we take a fraction in there like 1/3, that's 0.333 forever. Now, the first fraction, 1/4, terminates, it stops. 0.25 stops. 1/3, 0.33, it never stops, but there's a pattern to it, right? It just keeps doing the same thing. An irrational number is any number that is a non-repeating, I can't spell, non-repeating, non-terminating. The most common example of an irrational number that you've learned is pi. Okay, 3.1415 keeps going, there's no pattern to it. Another irrational number that you may be familiar with is the square root of 2. Another irrational number that you may be familiar with is e. But when you're learning about numbers, a lot of times you're told that they're irrational numbers and you're given a few examples, but what you're not told is that there's actually more irrational numbers than there are rational, which is weird because I just said that there's an infinite number of these, right? Like, we know that there's an infinite number of rational numbers. There's an infinite number of fractions. So how can there be more than infinity, right? Well, it turns out that there's two types of infinity, all right? When it comes to infinity, there's two types. There's what we call countable, and then there's what's called uncountable. So the idea of countable is this. If I just tell you start counting, right? 1, 2, 3, 4, 5. That's a list of numbers that is infinite, right? Goes on forever. But you can find a systematic way to kind of proceed through the list. I like to think of it like lily pads on a pond. You got all these lily pads, and you're a little frog trying to hop across the pond, and you can hop from lily pad to lily pad. You're just never going to reach the other side of the pond because it's an infinite pond with infinite lily pads. But as you hop from one to the next, you are proceeding, like you are moving, right? Uncountable is such an awkward idea because what it is, it's this idea that you're trying to hop from lily pad to lily pad, but as soon as you make your first hop, you realize that you missed a lily pad. Actually, you didn't miss just one, you missed an infinite number of lily pads. So you try and hop back to one, and then you realize you just missed another infinite number of them. And so there's no systematic way to march across the infinite pond, because every time you try and move, you realize you forgot a bunch. And because of that, when you look at all the numbers just between 0 and 1, yes, there's an infinite number, a countably infinite number of fractions, but there are an uncountable number of irrational numbers. So you're nodding your head, which makes me think that it makes sense. But I've got the best analogy I have, though, and this one works. You're allowed to use
One
this.
rational number, there are countless uncountable, or for one
The
countable.
irrational numbers are uncountable, and the rational ones are countable.
Mhm.
Okay, so basically any set that's countable has what we call measure 0. So if you can count the set, it has a measurement of 0. If it's uncountable, then the measure is not 0. And so the probabilities are based upon the measure of the set. So when you're asked, what's the probability of picking a number out of there that's a fraction? Well, you say, well, how big is that set? That set has a measurement of 0. Okay, how big is the measurement of the irrational numbers? It's 1. So the probability of picking an irrational number is 1, which is 100%. So, okay, but here's a really good analogy. If you've ever been like away from the city at night, right? And you look up in the sky at night, right? You just see all these stars everywhere, right? Stars, almost, it's like you didn't even realize there were that many stars out there. Okay, so the stars are the rational numbers. The stars are the fractions. And it just seems like they're everywhere, right?
Mhm.
The irrational numbers is the black, is the dark, okay? So could you point to a star? Sure, right? You could say, yeah, there's a star right there. You can start trying to count your way through the sky with the stars, right? But if I asked you to start counting the black, you couldn't even point at one. Like you couldn't point at anything, but it's there, right? Like it's there, but it's taking up a majority of the space. And so the equivalent thing here to this question that I asked about picking a fraction would be like if you had this perfect pointer, right? And I asked you to close your eyes and point into the sky. What's the probability that you're actually pointing exactly to a star? Or do you think you're going to be hitting black? You know what I'm saying? The only way you can actually point at a star is if you intentionally point at it. That's like, if I want to go pick a fraction, I can go get it. I have to look for it though. Oh, there it is, 1/2, I can get it. But if I close my eyes and reach in and pull it, I'm not pulling a fraction. Does that make sense?
Does.
Yeah. So I think the best I can do with it.
No, it definitely does. The star analogy definitely helped a lot.
Yeah. Yeah, that stuff you wouldn't get into unless you were a math major usually, or I don't know. I mean, it's not too far out there in the, I mean, you do learn about, it's called cardinality, and that's like computer science people, they do talk about sets and the measure of sets. I don't know how deep they go into it, but it's kind of interesting because in graduate school, you know, I had to tutor, and that means like going to the university math tutoring lab and just sit there and wait for people to come in with questions on math. And the tutors that they hired were usually graduate students in math and graduate students in computer science. And the reason why is because when you get to the graduate level, math and computer science are essentially the same thing. It's logic. Like, it's just like, it's logic and it's rules and it's theory. You know, does that make sense? So there's a lot of overlap in computer science and in some engineering that you do get into the measure theory and things like that.
Sure. Yes, I'm studying electrical engineering, so I'm pretty sure I'm probably maybe going to run into that because a lot of
I don't know with electrical how deep you get into this sort of thing. This is actually called Lebesgue measure, and it's kind of like the standard. I know for me, I didn't see it until I got to courses called real analysis, and I'm not sure that engineers take any courses like that. Not to say that you won't be exposed to it in some sense, but I'm not sure you'll study it in depth. You might just be told that the rational numbers have a measure of 0, and so the probability, you know, you might just be told that, but you don't really actually get into mechanically trying to prove any of it. You just kind of like, oh, we need to know that, you know?
Sure.
Yeah.
Well, thank you. I really do appreciate it.
No problem. Any other questions or anything?
I had a, can you hear me?
I can hear you, Sarah.
I'm sorry. I had a question. I was exploring Canvas and I saw in the discussion section that there is like a bonus to
There's a bonus
caption your videos. Yeah.
Oh, it's still there. I forgot to take that down a long time ago.
Okay.
Yeah, I know what you're talking about. I'm gonna have to remove that because it's already been done. Yeah, a couple of semesters ago, I had a student who was hearing impaired, and so even though YouTube does closed captioning on videos, we all know that it's not that great. It's not perfect, especially for math. So I tasked my class as bonus to close caption my videos for me, and they did, and I was able to give that to them. So, but it's in the discussion board.
Yes.
Okay, I'm gonna have to go in there and take that out because that's like over a year old, I think. And I think what happens every semester, I copy my course over and just copy it and then change things. And so I think what happened is I didn't realize it was in the discussion board, so it just came over. So thank you for pointing that out. I will, I'll get rid of it. Anybody else?
I was trying to access the ebook, and it said there on the, like, do we have to pay for the book still, or did that came in like with the tuition?
Yep, it came with tuition. So in WebAssign, is it prompting you to pay?
Yeah, it's kind of saying like, oh, you're on like a free trial kind of basis to like September something.
No, don't pay. Don't pay for anything. Yeah. Yeah, don't pay for anything. They told me that everything was good and that everyone should be taken care of. So yeah, do not pay for anything, because then we'll have to go and get the reimbursement and all that. I'll send the WebAssign people an email later on today, or I'll probably wait till tomorrow, and just say, hey, just double check that all my students are good. Don't, you know, they told me everything was set up properly, so it should just let you know. Has anyone else tried it?
Yeah, it did that to me at first also, but the next time I logged in, it came up with the regular status and let me use it without the
Was that
trial.
the first time you went in, Jane?
Yeah.
Oh yeah, it was my first time. I did it like last night.
Okay, so maybe Coleman's saying that, you know, maybe the second time you logged in, it might be cleared up.
Oh, I'll try.
Okay.
Thank you.
Have a good weekend.
All right, you too. Thank you. All right, German, you good? You got a question?
No, no questions.
Okay. Is that speaker in the background? That my voice isn't coming through that big speaker in the background. All right, man. Have a good weekend.
Thank you too.
Okay. All right. Bye-bye.